we are going to talk about sheaf cohomology. So sheaf cohomology involves, at a certain level, dualizing what we just saw, but it's more subtle than that. And it's worth discussing something that's closer to that in terms of simplicial cohomology, where we're dealing cohomology involving simplicial complexes. And then we'll talk about it for sheaves. Okay, so you'll recall we have these chain groups, and oh my goodness, again, I should have gone and taken this picture of the chain complex just to remind us. Okay, somehow screwed that up. Okay, let's copy this and we'll put it in here. Come on. Okay. There we go. Okay, so we've just been talking about the chain complex for homology, where each of these are associated with chain groups, associated with these free abelian groups, where the basis is given by the k simplices, and we can have any integer amount, including negative amounts, of each k simplex. Remember that as coefficients? And equally well, each of these is associated with a vector space, where the dimension of the vector is the number of k simplices. So we're talking about for dimension k. The dimension of that vector space is given by the size of the basis set, which is the number of k simplices. And a given vector in this vector space will have specific integer elements given one for each of those basis vectors, or one for each of those bases, one for each of those simplices, right? That tells us how much of that we have in integer terms. We remember this, right? We're good with that. Okay. Now, we're going to define for simplicial cohomology, we're going to then go to sheaf cohomology. Simplicial cohomology, we're going to define a K cochain group, okay? And instead of going down here, do you remember we went from like dimension 2 to dimension 1? This was our triangles, remember that? Dimension 1, this was our edges. Do you remember that whole story? A, B, C differentiating to B minus A, and so on, down to 0, and then we couldn't go any further. We're going to now be going up in dimension, okay? We're going to be turning these things around. Actually, we're going to be transposing. Going from C sub k to C sub k plus 1. We're going to be dualizing it, taking the dual, right? Up. We're going to take the up. And that's going to put, as I understand it, it takes the transpose of each of these. Okay. So what's going to happen? Well, look, if we apply the co-boundary operator, oops, this is, I stand having made a horrendous mistake. This should be going like this. Keep an eye out for whether it's a subscript or superscript. Superscript will be cohomology. Subscript will be homology. So we have a co-boundary operator. It goes up in dimension from C upper K of X. Those are all the K chains in our simplicial complex X. and it'll go to this k+1 chains in our simplicial complexes. Okay. And if we apply this co-boundary operator to a K simplex, sigma, we'll get a k+1 chain. What k+1 chain? Well, it's a sum of all of those k+1 simplices tau that have sigma as a face. So sigma is a face. Maybe sigma is one of these. Maybe it's AB. In which case, if we're mapping it up with a co-boundary operator, we'll include this two simplex. Okay. So it kind of finds the preimage of the boundary operator. It goes up to all the things that were mapped down to sigma. So ABC might be found by ABCD, be mapped to, and these should all be with capital oops. Okay. AB might have been included from ABC and ABD. Okay. So it follows it's a linear operator. We know how to apply it for simplex to get a k+1 cochain. We're now going to apply it for a whole sum of these for the entire cochain, and we applied for each of the simplices. Okay. So we're going to have cochain complexes, and somewhere in here, I can't figure out why I didn't do that. We have a cochain complex, and it's going to go successfully up in dimension. And we have this nice property. You may remember a variant of this property from before. Remember that? Taking the derivative twice because of symmetry led to 0. Well, it's a similar thing here with similar cancellations, just going up in dimension. We can define a K cocycle kernel group as the kernel of the co-boundary operator, like the things mapped to 0, going up in dimension. And we can look at co-boundaries in a group co-boundary. And we can define here for simplicial cohomology cocycle that is not a co-boundary for this. Now, I'm not going to try to interpret that, but the whole picture is dualized here. I think these have some interpretation, but what I really want to talk about is sheaf cohomology. This is a really useful thing. Now, when we go to sheaf cohomology, it's going to involve getting us to adjust our understanding. And I want to review so you may remember from last time that with simplicial sheaves, do you remember that our sheaf mapped each simplex, simplex, so vertex F, mapped it to a stalk, it associated with a stalk, right? So vertex F might have been associated with stalk in above it of possible values that we have there. Maybe it's it's drawn from three-dimensional real vectors. So this might be number of people with chlamydia, number of people with gonorrhea, number of people with herpes simplex virus. We might have a different stock associated with D. Maybe it's just the temperature outside or something like that. That's not only true for simplices, it's also true for these higher simplices. So it's not only true for vertices, I should say. It's true for higher simplices like DE and CDE. Each of them is associated with a stalk. Do you see them? Do you see these stalks? Yeah. Do you remember this from discussing of co-sheaves? I'm sorry, of cellular sheaves. And do you remember that each of these maps here was associated with a mapping here? Okay, this is going to be important for just getting us oriented. What we're going to do here is we're going to have a cochain complex. And my goodness, I am going to go and copy this so we have it right early and we can refer to it often. Here we go. It's going to look something like this. Each of these CK for sheaf cohomology, and notice I put an F here. That's the sheaf. See this F? Each of these guys will be a vector space. But, and this is super important, it will no longer just be a vector, it will no longer be a vector space of whose basis is given by the simplices. Remember we had that? Remember when we had the chain complex? Each of these was a vector. I kept on emphasizing it. Was a vector where the basis for that vector space, the things that form sort of the coordinate system, as it were the simplices of that dimension. Do you remember that? Remember that? Just a few minutes ago. So if there was one triangle, one thing of dimension 2, one simplex of dimension 2, the vector space here would only have one dimension. It would only be a question of how much of that one triangle do you have? 0, 1, -1, 2, 3, right? By contrast, maybe the triangles ABC, and maybe here we have the basis. This is for chain complex, remember? For homology, we might have AB, and we might have AC, and we might have BC, etc. And here we have a vector of 3 things, and we're saying how much of each of those one simplices do we have? Do you remember this? Just want to make sure people are following along. That was chain complex. That's what we were doing just before I stopped recording. Are we good with that? And we had this mapping down, finding what are the boundaries of the triangle. Okay, so now with sheaves, we're not going to have C upper K indicating that anymore. What is it going to be? It's going to be the stalks over each of those K simplices. Sorry, so let me say that again, because I need to emphasize. C upper K is going to be associated with the K simplices. I'm not saying count of K simplices. I'm saying simplices of dimension K, right? Maybe K is 2. Maybe there's only one of them, the triangle, let's say. Maybe there's only one triangle or diagram, in which case there'd only be one simplex to consider. But the vector is, the basis of the vector is not the given by the K simplices, the simplices dimension K. It's given by the stalks of those. So maybe that dimension 3 simplex has itself a dimension, the stalk over it, a dimension of 1, in which case it will be that space over C2 will be of one dimension 1. It's a vector with a single number in it, namely this real number. But it'll be a real number. It won't be an integer. Okay, but now let's consider our dimensions. Let's consider our 1 simplices, or simplices of dimension 1. We were just talking about this. It's going to have a stalk over it. C sub 2 here is going to be consisting of vectors of real numbers representing the value in the stalk over the triangle thing of dimension 2. For C sub k minus 1, what is that going to be? Well, now this was dimension 2. This is going to be dimension 1 things. Well, what is that going to be? What is C upper 1 going to be? What's the vector space going to be? Well, it's going to be a vector space formed by a concatenation of vectors for each one-dimensional simplex. So let's list them out. AB, that's going to be R2, right? It's going to be a pair of vectors. We have BC, that's just going to be a single real number. So we're going to have R2, and then we're going to have R. Imagine we're going to have this big vector, and the first 2 items might be from AB. The next one is from BC. So the first 2 are a pair of reals, one after the other in the vector. So the vector of 2 elements for those, 1 element for this guy for BC. Then maybe we'll go to BD, and then there'll be reals. And this is going to be in some canonical order we'll talk about in a moment. And then 1 for AD and 1 for CD. That's going to be R squared, R to 2, and for DE, R squared. And so at the end of the day, this is going to be a big vector of possible values. So the vector space for this will state all possible values the K simplices could take on. All possible values the K simplices could take on. Why are we interested in it? Because the global section will be some subset of those, right? Okay, so C upper K is going to be a vector space associated with the stalks over the K simplices. C to the K minus 1, C upper K minus 1 is going to be a vector space given by the data from the stalks for all the K minus 1 vertices. Same for C sub K plus 1. Okay, so what does the co-boundary map do? Well, what it's going to do, this is going to be really cool. It's going to map this data for simplices of dimension K minus 1, maybe those are for your vertices, up to, so that's going to be the data for those. And it's going to map it up to data for the edges in that case. So if these are vertices, we map it to edges. And what's that going to do? Well, that's going to take the difference between what's implied by one value here when you map it up for vertex A and another for vertex D, and take the difference and make sure it's 0. and we're going to seek it to be zero, that difference. So we're going to take one minus the other. I mentioned the orientation will come back this -1. That's where it comes from. Okay. And we're going to build up this chain complex, and its zeroth cohomology is going to be the global section of the sheaf. Okay, so I know there's a lot going on here. Let's unpack this. Let's unpack it. Here we have our simple simplex, right? Okay. Here's our simple simplex in our map, right? You remember our maps, right? These things? Let's look at this one right here. Are we okay with that? Get this one? I think it's that one. Let me make sure. A and D. It's A and D. Oh, it's this one right here. This was our original simplicial complex. See our edge there? Do you see that? Do you see that edge? Okay, I think you're comfortable with that turning into this. Do you remember that attachment diagram idea? We actually reify this edge. We say, wait a minute, this edge ain't just some lowly connection between A and D. It's not just some random connection. It's a thing in and of itself of interest. Call it AD. Remember, that's a simplex, right? AD is a simplex. It's a thing, just as much as CDE is a triangle. So AD is a two simplex. Or sorry, it's a one simplex. Excuse me, right? So here's our one simplex. We break it out explicitly, right? And you'll notice that this A is attached to it. We comfortable with that? D is attached to it. We comfortable with that? Remember we wrote it with this weird squiggly arrow? I don't know if you remember that. Took me a while to get that squiggle right. Okay. We okay with that? So this was our simplicial complex. We dignify this edge with a simplex all its own. We know it's called AD, and we reflect it in this poset associated with this attachment, right? Okay, that's what we're starting with up here. This is in the simplicial complex, and then we turn it into this, right? There's our squiggle things, right? We have a squiggle here, squiggle there, squiggle, squiggle everywhere, right? Okay. And now we apply F to it to get the farm. For old MacDonald had a farm. No. So here's the F, right? F, so we're going to apply the sheaf functor, right? We're going to apply that. Remember the idea with the sheaf? Do you remember? The idea with the sheaf is we associate a stalk over each of those. Do you remember that? So there's some stalk F of D over D. There's some stalk F of A over A, right? Do you remember that? In this very room, not long ago, we talked about that, right? Associating data with every point here. Are we good with this? Are we good with that idea? And we did it not only for the vertices, we did it for the simplices like edges, right? We have data for them. We good with that? Okay. Okay, watch this. Keep your eye on the ball. We're going to associate data with each of them. So all I'm showing is how that data got associated with each of them, right? We have some data here, data there, data everywhere, right? Okay. Now, for a sheaf, we know that we don't want any old maps here. We don't want any old assignment of data here. We need data that gives a consistent picture here. Remember, think about those pictures of Alaska. They have to overlap, and where they overlap, they have to show the same consistent picture, right? If we have data for cities in northern Saskatchewan, all the way down and including Saskatoon, and we have data for southern Saskatchewan up to and including Saskatoon, they have to agree on what they depict for Saskatoon, right? So with a sheaf, we needed the picture coming from A down to AD to be the same as the picture coming from D to AD. Okay? So what I'm saying is whatever data is assigned to A, if we map it up to AD, we have to get the same data as if we have data over D and we map it up to AD. And this is a map here with the squiggle. It's a squiggle map. Okay? Okay. So look, we need this to equal this. I'm going to subtract this from this and say it has to equal 0. Right? I mean, that's what this is. We're operating with data. For example, with vector spaces here. We have vector spaces associated with all these things, right? All these vector spaces. I am going to, this is some vector. This is some vector over the data for AD, right? So if I have this vector and I map it up to this, and I map this one up to this, both cases, they give me a vector over AD. Look, the vector over AD, just trace it right over. It's a single number, right? It's a scalar. Let's get a real scalar. Okay. Okay. So this minus this equals 0. There needs to be no difference between them for them to be equal. I could write that in matrix form as put SA here, put SD here. This is the data from the vector space over A. This? Yeah. Oh, it's divided into 2 parts. That's all.
Just make it clear that
just
there's a space.
That there's a space there. Yeah. Yeah. It's just showing it in 2 halves. Sort of like this half comes from this half comes from this, right? And so when we think about doing the matrix, vector matrix multiplication, right? It's SA times this and SD times this. The fact that it's divided that way, Uchiha, makes it clear that this guy goes with this guy. Because otherwise you don't necessarily know that the number of columns in this match the number of rows here. And so it's kind of a nice diagrammatic. I could have drawn a horizontal line here, but okay. So this times this minus this times this. Where did this minus go? This is our old friend, the minus. This is the -1 to the I that we knew in, well, maybe some of us loved it, some of us hated it, but we knew it. This is the same minus. This is the same stinking minus. Like that's our minus. That's our minus sign. Might as well embrace it. It just comes out here as saying that these two have to equal that one. Okay. So that's the idea that we're going to be going on. Let's unpack this a little bit. The co-boundary maps here. So we have this co-boundary maps, which are of this form. I'm calling them D. There's some notational difference. This says delta, and I think in Rosiak he calls it delta upper. I'm gonna follow Robinson and call it D, just so I'm consistent. Robinson uses delta for simplicial cohomology, but in any case, you prefer to think of this as D. Okay, so the idea here is what does this mapping look like? Well, I'll tell you what it looks like. It looks like, you may recognize these things. Those are just these things right here. And some of them have a minus side. What determines if it's a minus sign? Or what determines if it's absent at all? Well, look, if A is not within B, if A is not a face of B, if K simplex A is not a face of K plus 1 simplex B, this is 0. We don't have to worry about it in our co-boundary map. Remember, co-boundary map is going up in dimension. This is -1 to the I if K simplex A is produced by deleting the ith vertex of B. So if A is a face of B, Remember that whole idea of being a face of something? Remember we said like with faces, we like C ED is a face of CDE by virtue of deleting C. Remember that? Each of these faces here was deleted, was obtained by deleting a vertex. Do you remember that? So like this face EC, which vertex was deleted to get EC? D. Yeah. So that's true in general. It's not just true for triangles. But in general, if A is a face of B, it can be produced by deleting some ith vertex of B. And all we do is take -1 to the I, okay, to get that here. And that gives for some the minus sign and some the plus sign. Now, that minus sign is going to be what enforces this constraint that the restriction maps are equal to 0. I'm sorry, or equal to each other. Is the fact that if you take one, if you add them up, they all have to be equal. It means the differences between them are all 0. And that's what this actually enforces. Okay. So again, unpacking it, each of these items, so the co-boundary map is composed of these blocks. It's composed of these blocks, one for each of these sort of things. What does it look like? Well, I'll show you what it looks like. It looks like this. This is what it looks like. And in fact, really, by all proper accounts, that should be located right here in the slides. This is based on a really nice presentation by Michael Robinson. And I need to give him credit that he inspired this. So the idea is that we have this big matrix, and it's going to have entries here, either +1 or -1 or 0. Most of it's going to be sparse, but if we have column J, that's going to specify the possible face of B that we're considering. And let's put it this way, if we have K + 1 simplex B sub I, and we have K simplex A sub J, then the ith row, jth column entry here will give either a 0 if A sub J is not in B sub I, or it'll give a +1 or -1. And that's exactly what's going on here, right? D is within AD, so it gets either 1 or -1, and it gets a -1 because of the rule there with the signs. Same thing with A. All the others are 0 associated with that. Okay. So this co-boundary matrix is this block matrix like that. Okay. What is CK? Well, I told you it was sticking together, sort of concatenating together the stalks over each of the K simplices. So C to the K upper power for a given sheaf is sticking the stalks. So it's forming this vector space whose bases are the bases of all the stalks for the K simplices. So it has values for each of the K simplices for their stalks. This is called the direct sum operator. And basically it means what's over a case. If we consider CK, what like the things that are sitting over, remember this idea of bundles. Like we have imagine you have the K simplices down here at the bottom. And over them, over the K simplices, So the k-simplices are here. Over the k-simplices are the stalks for each of the types of k-simplices. And we're going to stick them into a big super stalk. It's like Jack and the Beanstalk. It's like a super tall stalk, right? No one seems to like that. Okay. It's like a super tall stalk. And in that stalk, there's going to be something for each. There's going to be the stalk of each K vertex. It's going to be stacked there. It's going to be stacked up there. And that's what this is. This is one of these giant super stalks sitting over the K vertices, giving all the values you can have, the vector space of possibilities for all K simplices, for all simplices of dimension K. Now, you got to be really careful here in your thinking, because that's a vector space which has a certain dimension. The dimension of that vector space is not K. No, it's the K simplices we're dealing with here. The stalks over the K simplices, well, my goodness, the stalks over the one simplices we just said, what dimension is it? Well, it's go through and count the one simplices. EF is of dimension 2. So the stalk over that would be R squared. Stalk over DE would be 2. So I'm doing a running tally. 2 plus 2 plus 2 plus 2 plus 1 plus 2 plus 2. What am I doing? I'm adding up the dimensions of the stalks over each of the one simplices. And it's going to be some big number. And that's going to be the dimension of the vector space over CK. Okay? So what we're showing here is the boundary map here, which is going to be taking the data. This is an extremely important point. It's going to be taking the data over CK, the data assigned to each of the K vertices, and it's going to be mapping it to the data over K plus 1, making sure everything equals 0 here. So in other words, we're going to be, well, I mean, that's what we want, but basically we're going to be taking the differences. We're going to be considering for each simplex of dimension K plus 1, we're going to be taking the difference between what it's being told by the data associated with the simplices of dimension K in turn. That's what's going on here. Okay, so I think what might be helpful is at this point, I could go on and drone on about those things, but here's do you recognize this up here? This is our cochain complex, a sheaf cochain complex, right? And I just said the CKs of all these verses. Let's see what it looks like. Can we see what it looks like? Well, okay. We're actually going to be considering cohomology over it. We're going to be considering the kernel and the image, but let's just go back to basics here. What are the dimensions of these stalks here over 0 simplices? Well, it's concatenation of all the stalks over all the 0 simplices here. Okay. Here we go. So I've labeled, here's simplex A. We have some data over it. What's its dimension? 2. We have data over B. What's its dimension? 3. We have data over C. What's its, where's our C? There we are, 2, right? There's data over D. What's its dimension? 1. Data over E, dimension 3. Data over F, dimension 3. I didn't do the running tally, but that's a pretty big stock over that. And then we have a co-boundary map here. Up to this dimension 1. AB, AC, BC, and each of those has a vector space over it, right? This mapping is a linear mapping. It's a vector space. It's a big one, but it's a vector space. This is a big one. This is a big one. It's a vector space. And what we're going to be doing in our co-boundary map is taking each of these and looking at its discrepancy when we map it. So let's take one particular one. I'm going to look at DE. Can we look at this one here? Can we look at this one? DE, see that one? So let's focus in on that. In fact, I'm gonna copy this, which I put in the next slide, and I'm gonna put it there. So we can just go highlight this. So we're gonna focus on this little one. So what is this one gonna use? Well, look, DE is down here. The computation for the data over DE, it's going to be based on the amount it's getting from E and the amount that it's getting from D. So we have some data over D. What's the dimension of data over D? 1, right? It's just a single real number. We have data over E. What's the dimension of that? 3. It's a triple of real numbers. All right, so those are going to be values here in this long vector. Okay, we're going to multiply that by this matrix, which here is called delta to 0, upper 0. I called it, Michael Robinson calls it D to the upper 0 to distinguish it from simplicial cohomology. Okay, so here we go. So what we're going to have is we're going to have a big honking matrix. I'm just showing part of it. This matrix is going to have a component for D to DE and a component for F to DE here, okay? Basically what that's going to do is it's going to take the data assigned to D, it's going to multiply it by this to translate it by this 2-by-1 matrix. Looks like a vector, but it's good to think of it as a matrix. A matrix operates on vectors. It multiplies vector to get another vector. So we have a kind of rump vector here, this single number, and multiplies by this kind of rump matrix here to get a quantity in R squared, right? So a scalar times 3, 1 is going to give a value in a pair of reals. And for R3, it's going to be this matrix. See that right there? And by the way, that first one is with a minus sign to get the minuses correct. And then this one is going to be multiplied to get something of R3, right? If we have a quantity of R cubed and we multiply it by this matrix, each of those elements is going to be multiplied by this, and same thing for this, and we're going to get a 2-by-1 matrix or vector out. There we go, 2-by-1, and we need these two to equal 0 is what we want for the 0th cohomology. I know I haven't gone and drawn, but remember the 0th cohomology, you may remember, it's just because there's no k-1 boundary k-1, this should be D here. Because there's none of this, I'm going to cross this out with a strike through, right? It doesn't exist in this case. All we're dealing with the kernel. What is the kernel of a matrix? It's the values it sets to 0. So what we are dealing with is here, we are dealing with a matrix here which basically is set up from all these to make sure that the difference between the values mapped to the higher dimensional simplex from the lower dimensional simplices are all equal, in the sense the difference between the two is zero. That's what's going on here. But it's going on for each and every one of these simultaneously based on each of these. So we've just zoomed into a microcosm. What does the entire thing look like? The entire thing looks like this. This whole thing, remember I told you it was a block matrix? It was one of these as well. In Daniel Rosiak's, he's showing the block matrix. Look, here's our lower dimensional simplices. Those are going to be multiplied here, right? We're multiplying. This is on the right here when we multiply it. So each of these is going to multiply S of A, S of B, S of C in turn. And what we're going to get out is going to be some result for each of these simplices here, these data. And that's going to be what results. So what we were just looking at was this particular row. That's what we were showing. Just zoomed into this microcosm, how it multiplied by DE. DE, I should have shown. Well, we're getting out DE based on the values for DE. We're getting out the value for the simplex DE. So this is this big matrix, and it's going to multiply this big vector encoding the data for the vertices and get out data here for the edges. But more than that, it's enforcing. We're looking for the kernel. That's what zeroth homology involves. We're looking for the kernel of this. The kernel of this means the values that are mapped to zero by this, which means the values for which this times that equals that times that, and with which this map gives the same information as this map. In other words, if we take this map and we subtract it from what we get for this map, we'll get zero. That's what it would mean for this little bit to be part of the kernel. We want this whole thing times this. So when I say times, it's over here, times this to equal to zero. That would tell us that for all of the one-dimensional simplices, they are getting consistent values from each of the vertices. That's the setup linear algebraically. Now, this doesn't just happen there. It actually happens at higher levels as well. But we have to consider there the image. So really, I did a disservice by showing this. I should have said zeroth cohomology. That's when that disappears. For the kth cohomology, we actually have to consider the image. And the interesting thing is this kernel mod image, this is done in the vector space associated with the stalks now. But for the zeroth, what we get is this. We get this, we get this, and what is that giving us? Yeah.
Boundary matrix actually is just a subspace of zero cochain.
That is correct. That is correct.
That is satisfying the
That's right.
zero local inconsistency.
That's right. Yeah, it's a subspace of this such that if you multiply it by this big honkin' matrix, or the vectors over here, so you multiply it, so the vectors on the right, you multiply it by this, you'll get zero, right? That's the zeroth homology. And by zeroth homology, remember, we want we're finding the kernel of it, meaning it has to equal 0. Why in the world do we want to do that? Because those are the values here that when they indicate values for the things of dimension 1, they give consistent picture because 1 minus the other is always equal to 0. They're always giving a consistent picture. That is the global section for this sheaf, is the values of these stalks over the vertices that where they're in the kernel of this matrix. Now, this may sound weird, but here's the thing. This may sound, complex, but here's the thing. Computers are really, 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 really good at doing matrix algebra. And there's very high performance code to do matrix algebra, even with very large matrices, very large vectors. And you can compute the kernel of a matrix very readily for even extremely large matrices. And this gives us a way of computing the global section for the sheaf. It is precisely the 0th cohomology group. It's given by the 0th cohomology group for this. It's given by the kernel of this matrix. That will give a consistent picture for all of these things. Now, you can go further than that, and you can look at first cohomology, second cohomology. Michael Robinson talks about, and I think this is also something which others have written about. When you try to identify obstructions, try to identify pathologies, or you try to, when identifying obstructions is you're trying to figure out what is not matching up. And actually, you can do those things here. You can look at what's preventing there from being able to compute the kernel. Why is it you're unable to compute the kernel? So this, well, it may seem like, very one thing built on another, built on another. This gives us a way of solving for sheaves, the global section of sheaves, rather, and identifying obstructions to finding that global section, finding where you can imagine, like maybe you cannot find the kernel for this matrix because of reasons you trace down to a few entries here. And that is going to let you potentially refine your sheaf to allow you to identify data that would be consistent. So let's step back for a bit. We're over into our third hour here. That's okay, because this is our meeting time for ACT stuff. But I'd like to talk here, zoom out for a second, and say, look, we've talked today about two things, which have a certain deep similarity, but certain differences. We've talked about homology and sheaf cohomology. Let's compare, because your heads are probably spinning. Homology, we had chain complexes. In fact, I put them down at the bottom here. I don't know if you can see that. Do you remember? There. I tried to hide it over at the side. Okay. Homology, we have chain complexes. This is what they looked like. Do you remember this? Where we were dealing like CK, the vector over CK had an entry for each K simplex. Do you remember that? Do you remember with chain a chain complex for homology. We weren't dealing with some stalks. We were just dealing with a vector with an entry for every K simplex. Do you remember that? Okay. And we wrote that as C, I don't know what to call this, under dot of X with a chain complex like this. Boundary maps just mapped, do you remember this? The boundary map mapped a simplex of dimension K, like our triangle, our solid triangle, CDE, down to its boundaries, its faces, right? Like CD and DE or what have you. Do you remember that? That's what we had for chain complexes. The chain space here had bases. So we had vectors and their bases, one entry for each of the K simplices. Okay. Okay. Here, the homology was given by the kernel of delta sub K, which took like a higher a K simplex into a K minus one simplex, like a triangle into its sides, take into account orientation. The kernel of it, like what things map down to zero that didn't come from a higher level dimension. So there might have been, for example, some loops that were in there of dimension K, maybe it's K is one, and they're cycles in terms of edges. And we're interested in them. We're interested in those cycles, but we don't want we don't want to consider cycles that are just produced from taking the boundary of triangles of two simplices from the dimension above. We're not interested in those because those weren't in our original complex. Those are coming from the dimension above. So the one homology here would give you the number of loops in the data, or sorry, number of loops in your complex, which is something that's of interest. Not the loops that were produced only by taking the boundary of higher level things. No, we're not interested in those. We're interested in loops that were there from the start. That's the idea. Sheaf cohomology is dealing with a co-chain complex. That's shown up here. And a key understanding is that we are taking things at lower dimension. Imagine like the data over the vertices. We're mapping that data for those vertices up into data over the edges and making sure everything lines up. We're taking the kernel of that mapping, to make sure everything that's implied by the vertices in terms of the edges to which they're connected, they're telling the edges consistent things. That's why we're taking the kernel of it, right? The kernel of that. And our biggest interest super strong interest is in H0, where we don't have to worry about this image thing. We're just worried about the kernel. We're just interested in the global section, the assignment of data over the vertices that give a consistent picture, that tell the same story to the edges. Because all the restriction maps start at the vertices. And we have to get that right. There are interesting things for higher dimensional cohomology, but this is the main thing. This is what you're solving for often with deep learning. It's what you're solving for the zeroth cohomology, the global section. If we start to want to understand the abstractions, we can do that some there, and maybe the higher cohomologies will help as well. Okay. What are we doing here? What are these co-boundary operators? Well, they're the ones that take the data for dimension, say, K minus one, and turn it into discrepancies for what we are hearing from K minus one things of dimension k here from things of dimension k minus 1. They are mapping not the vectors over C sub k are not, again, they do not have here for the sheaf cohomology a basis given by the simplices. No, their basis is given by the concatenation of the stocks over the simplices of dimension k. That's what the vector space is for C upper k. To say that again, the vector space for sheaf cohomology, for both chain complexes and cochain complexes, we have vector spaces over, C for K. For homology, where we have chain complexes for homology, those vector spaces have a basis given by the simplices of dimension K. There's one entry in that vector for each of the simplices of dimension K. For sheaf cohomology, we, instead of a vector space that's associated with the data associated with those K simplices, that data is specifically from the stalks of those K simplices. So the vector space here has as its basis the concatenated basis for the stalks of each of the simplices of dimension K. And the co-boundary operators are mapping that data for dimension K into data for dimension K minus 1, specifically the data about the discrepancies between what we're hearing from each of the things in dimension K, because we want to make sure the discrepancy is 0, that the kernel of that is 0. The kernel mod image. You may ask, why are we taking this mod image thing? Well, for dimension 0, it doesn't matter. But higher dimensions, what does this do? Well, it just says, look, as I understand it, as Michael Robinson explains it, look, it's saying we're interested in making sure that the kernel is equal to 0, or, we're interested in the kernel, which are where the discrepancies are equal to 0. And we're not terribly interested in things we already computed at lower dimensions. That's why we take the image of it, or things that came from earlier dimensions. We're not so interested in. I don't fully grok that.
Yeah, you may understand that it's like some information get lost in your computation, and the image is like the true actual for the entire information, and that's why
That's interesting.
Yeah, that's why in the paper,
Yeah.
Thomas paper, is that
Yeah.
they have you can define a derived function, like you can
A what?
multiply something with the homology to get the full entire information on something.
Okay, that's interesting.
Information and actually.
I mean, certainly this modding out is modding out by this is choosing to put aside information from other dimensions that came up. And maybe what you're saying is you don't have to do that. You can accumulate all information potentially. Yeah, that's interesting. But I'm sure there's some insight there that I've yet to have. Now, sheaf cohomology lets us identify global sections. It lets us give an understanding of why so it lets us solve linear algebraically for global sections by taking the kernel of a matrix. It lets us identify obstructions that are preventing us linear algebraically, identify obstructions that are preventing us from finding a global section. Michael Robinson has also introduced a nice thing called a consistency radius, which basically takes data over which you've collected for a sheaf and identifies the closest global section that explains that data. The closest global section, and measures the distance from that global section. So maybe you have data for the world that doesn't line up exactly. It's not perfectly consistent, but this notion of consistency radius lets you find the closest fully consistent accounting, the closest one to the data, and measure the distance there. And I think actually for deep learning, what you're also doing is by iterating with the Sheaf Laplacian, you are trying to get to a global section with the estimated global section that can minimize the discrepancy. Yeah.
Or active points.
So it can minimize the discrepancy from data that you have. So sheaf cohomology is a challenging area, and I am told that it is viewed as being reasonably advanced material for those even in related areas of mathematics. I've heard comments to that effect, and that it is widely, it's comparatively few computer scientists who understand this. But once you understand that it provides an avenue for identifying Sheaf Laplacians used in deep learning, once you identify that it can let you compute global sections as linear algebra, once you recognize it can give you insights into obstructions, once you recognize that it provides an avenue for assessing the closest global section to your data, you begin to recognize that, in my view, the learning is worth it. Like it does take some constancy of purpose and fortitude to go through this. This is quite challenging material, but it's really practically useful material. And I will note that in a current deep learning context, it provides an avenue for really advancing more advanced deep learning architectures and solving problems that are otherwise very difficult, and doing so likely more parsimoniously, although I think more parsimoniously in terms of the computational effort, although I think the story, from what it sounds like, has yet to be fully elucidated there. There are some results I've seen that suggest that that's the case. But this is extremely current lines of work. And I think while this is somewhat fearsome, if you put your mind to it, you should be really well positioned from this to jump on to lines of like sheaf-based deep learning, which directly built on this. So this is sheaf cohomology, and this is as deep as we're going to go. It is a pinnacle. Some have argued that sheaves are one of the foremost creations of 20th century mathematics. Sheaves are one of the sort of pinnacles of mathematical abstraction, and they are also, in a contemporary context, extremely useful. But you've worked hard to come to this, and I know it takes time to sink in. I've been reviewing materials on this for many months. But hopefully this gives you some leg up in terms of some of the understanding I will note, for those aware of it, I have this large library of materials related to Sheaf learning, which vary from dissertations to videos to papers, a whole video series, really excellent ones by Michael Robinson, some by interesting ones by Robert Greist, etc. Maybe I'll make one other comment on this. You'll notice that we did this computation with vectors, right? We were operating with vector spaces, vectors for sheaves. What we're going to see, so we're going to have a bit of an interlude for Monday where we're going to be discussing growth and deep topologies. And that will be the last reading for this semester from the book. But it's on growth and deep topologies. And basically, they allow you to treat any category as a topology for the sake of putting a sheaf over it, which is really powerful. Maybe there's some slight caveat that it can't be an empty category or whatever, but basically you could take a category, treat it as what's called a site, and have a sheaf over that. And that's really powerful. The paper we'll be looking at first after that reading is co-authored by Ben Bumpus, Wilmer Leal, James Fairbanks. I think Matt Cafaro may be on there. I think he is, which is on a unified framework for time-varying data, and it's a sheaf perspective. And what this does is further allows us to not just have vectors over sheaves, but use C-sets as part of our sheaves. And this is a very powerful notion. And there are times where, in Michael Robinson's book, he turns categories into vector spaces in a process which he calls decategorification, to do the computations. And there's an interesting question for our work. If we use something like CATLAB, which can compute with categories, which can compute with C-sets, maybe some of the complex mathematical calculations used in vector spaces can actually be simplified by operating on C-sets, or generalized. Something to think about. And with those words, I think I will stop here. Now, where'd my Zoom go? Okay, let me back to that. Where's my Zoom? Is my Zoom still going?
So you're sharing the screen now.
Can you see my spreadsheet?
No, now it's the expression.
Okay, well, yeah, so this is my old laptop, right? This is because my new laptop is currently in the infirmary. Well, I've got to work on it. I've got to do surgery on it this weekend. So where'd my Zoom go? Zoom is like, I can't see Zoom. Oh, here it is. That's because I hit it. Okay, that's where it is. Okay.